that we can. I'm not sure if you still remember what we talked about earlier. So the most important thing is this AB line, the boundary condition. When we design, we need to make sure the reinforcement ratio smaller than the rho max.
Yeah.
And rho max is for this situation, the boundary condition AB. Then at this situation, the compression height is epsilon of Kc B H0. And this Kc, how to write this Kc? Is that it? No, that is Kc.
Something like this function.
I don't like this way. We know it's Kc. Kc B. So this symbol is how we define this symbol? Kc B equal to what? Remember?
AB is epsilon B. Epsilon B.
Kc B. See this symbol. Something like this. Something like this. A little difficult to draw these things. Kc B. Epsilon is easy. Epsilon is like this.
Yes.
So how we define Kc B? Kc B equal to who? Remember?
Epsilon C over H0.
Something like this.
Yeah.
So we need to make sure the reinforcement ratio is smaller than the maximum ratio. Then, or this here is XB, boundary condition, boundary compression height. So like this. XB equals to Kc B H0. And the Kc B actually we can call it a relatively bound height of compression zone. It's not dimension. It's not dimension symbol because XB is the dimension is or we use meter or something like this. H0 for the dimension and divided by this dimension is not dimension. So when we design, we normally make sure XC, the XC, C means compression to XC is the compression height. Compression height. Make sure compression height is smaller than what? Than this thing. Kc B is boundary conditions. So in other words, in this figure, that means if you want to design your structure is appropriate reinforcement, avoid the over reinforcement. You should make sure the compression height smaller than this Kc B H0 should be in this area, in this scope. once the compression height xc larger than this, that means your beam or your structure is over responsibility. That means you put too much steel inside. So here, the total height is effective height 0, h0. h0 equal to h minus as. And here, xc is the compression height. If the compression zone equal to Cb h0, that means it's the boundary condition. At this condition, with the increase of the load, what will happen for this beam, or the beam with the maximum reinforcement ratio?
The maximum reinforcement ratio.
Yeah, or at this boundary condition. Because boundary condition actually means the maximum reinforcement ratio. For this situation, when you actually the load on the or just the beam, what's the direct deformation or film is?
It's brittle. No, it's plastic. It's plastic. It's plastic. It will not both the steel and the concrete will break.
Yeah, it's a belong to plastic filler.
Yeah.
Still, the reinforcement reaches yield strength.
Yeah.
At the same time, the concrete reaches compression strength. So this happens at the same time. So that's the main thing talking about this. So we should remember when we design, we make sure our reinforcement ratio is smaller than the root max, or means xc smaller than Cb h0. And Cb, where can you find Cb? Remember? Or how to calculate Cb?
Yeah.
I remember we introduced the Cb. This is better. Cb, where is it? There?
It's X max. Yeah.
Cb related to the material, not including the concrete and the reinforcement. So why Cb related to material? That means once you have determined what type of the material you use, then you can check the code to find the Cb. Then when you know Cb, actually nearly or almost you know the Cc, the xb, because xb equal to Cb multiplied h0. Of course, h0. Before you know h0, you need to make the assumption of as. So that means when you define the material, then you know the Cb. So do you remember why we say Cb is related to material?
Because we use the strength, the Fc to calculate it. Fs.
I think it is from
Inside.
this way.
From the top there.
And we see there again. Cb is we call it the relatively bound height for the compression zone. So for the limit height of the compression zone, or the equivalent rectangular stress distribution, x equal to back xb. Then the compression Cb should, because Cb equal to x1 by h0, then x here x is the height of the equivalent rectangular block. So equal to beta xb divided by h0. Because beta we can find, also we can find in this table, it's only related to the concrete. So do you remember what's the definition of the bed? How we define this bed?
It was x times xc.
Beta equal to x divided by xc. So we introduce this, and finally we find that it's only related to the strain of the material. Then it's just related to the material. We can find this. And in this formula, one of the relation is this sense. xb divided by h0 equal to epsilon cu divided by epsilon cu plus epsilon y. So how we get this relation? Is it by the geometrical relation? Geometrical relation is from this figure. Can you write this relation? Now we say the xb divided by h0 equal to epsilon cu plus epsilon y. So we see this figure. So who can tell me why we got this relation? xb divided by h0. How? xb, this part equal to xb. xb equal to cb is 0. And h0 is this. Epsilon cu is here. And epsilon y is this one. From B to the on epsilon y. What's the mean? Y yield. The yield strength of the reinforcement. Because for this boundary condition, the reinforcement that reaches epsilon y yield strength, and the concrete that reaches the ultimate strength. So we got this. How we can got this from this figure? Can you write how we got this relation? Why this relation is equal or is not equal? Why? From this figure, how we can write this?
We turn it outside down. E0 over xb
h0 equal to what?
over xb equals. You turn it upside down.
We can take, for example, h0
Mm.
equal x0 plus the value which is downstairs. We can put the value of maybe b or x. h0 is a sum. Is a we put together x
xc or xb, xc or xb, xb.
No. That's x. The last one, yeah.
This one.
Plus.
Plus what? Plus
Yeah.
this one.
Plus this one.
So from here to here.
We can say c.
C.
Yeah.
Okay.
And then divided by.
Divided by what?
Divided by x.
Yeah.
By ac.
I don't pay
We can divide it by x. This one. Okay. We divide it by.
like the ultimate like that. Is it my C?
Because it should be proportional.
Okay.
This plus this one.
Oh, we draw this figure. So this is for the boundary condition, this for the property reinforcement, and this for the floor reinforcement. This one is epsilon CU, and this one, or this one is for epsilon where I H0 and this part we call A, B, C, D, E. We call this smaller A, B, C, this smaller C, B, E. So how to get this relation? XB, this is from the C, from AC, XB then equal to AC. AC, this part is the boundary condition, okay? This part is XB. Then this relation, how can I get this relation? Epsilon CU here, and epsilon CU plus epsilon Y, this part plus this part.
Actually, you said that the height, the E0 is.
H0.
When you use the word, I don't know if it's proportional, like half. You take half of. Like
Half?
not half per se, but like you say they are proportional, so you take from the top part and the down part. So you divide, you see the.
So we can write this now. How about this relation? epsilon y is this part. The reinforcement ratio, the yield strength,
So it should have been represented by.
For this part, I think you can't just
I think you should first like find maybe the LCM of this one.
So now the question is this part, epsilon b is 0, how can I get it to equal to this?
This one.
Yeah, epsilon y. Because b is 0. Because b is 0 is this length.
Yeah.
And then epsilon y is this length. So how you get this equal?
I don't know how I'll get it, but I know if this part has taken like the KCB is 0, I need to get the one from this part, but like that's a very, but I don't know how I'll get that for the S1 y. I have to find it.
That one you will just get H0 minus xb
A0 is
minus xb. You can quote it maybe PC or something. Yeah, that is
for the S1 y.
yeah.
Epsilon y equal to h0 minus fb.
No,
No.
S0 minus SB is that distance.
Is the edge of this triangle, one edge of this triangle, and epsilon y is another edge. So it cannot equal. It's just two edges of this triangle. So
So
it
like
is
this one too. I don't know. Last time it was
just this two.
this one
this
and
side.
this one represent this one. We need to find the distance from here to also here, which will also represent the CV. That's what I
I
guess.
see.
I know how to do it, but I've forgotten how to.
Actually, this formula, why we got this formula, it's just because this angle, this triangle is similar to this triangle.
To the AC.
AC, this triangle. This two triangle. That means for this two triangle, A, capital A, small a divided by BE, small BE, actually equal to AC divided by CE, something like this. This is the geometrical.
That is.
Yes. So basically, it's based on this relation we can get this. Is right?
Yes, no.
Okay. Because you get if you just inverse this expression is h0 divided by xb equal to epsilon cu minus epsilon y epsilon cu. So x0 we can use xb plus ce. Then this xb divided by xb is 1, x0 divided by x0 is 1. So now in this side only got ce divided by xb equal to this one is epsilon y by epsilon cu. So that's the two edge of this triangle. CE is this edge. epsilon y is this edge, and xb is this edge, epsilon u is this edge. That's this two edges, two triangle. So from this relation, we got if CB, we can calculate the CB.
Yeah.
So this process is just tell you how we get this value CB, because finally we can replace this symbol into like this format, and we can see inside is include the strength of the steel and the modulus of the concrete. So finally, we can find from this code according to the material reinforcement of the concrete. We find the CB. In this side, say substitute XB and epsilon y. Here is a epsilon y is the yielding strength of reinforcement. So FSD is the tensile strength or reinforcement, and the ES is the modulus of reinforcement. Then from this relation we can go to epsilon y is this yielding strength. The strength, the epsilon means the strength of the reinforcement when the strength reaches the yield strength. So replace this epsilon y and xb into this relation epsilon y xb, and finally you can get CB equal to this. So xb equal to CB h0 divided by s. So how we got this? Because beta equal to x divided by xc. CB h0 equal to xb. Here is something wrong. It should be CB h0. CB h0 it should be this part xb.
From the A to C. The triangle to C is equal to CB.
Yeah. So this, here maybe something wrong. We find it here. CB equal to x divided by h0 equal to x equal to beta xb divided by h0. So CB here xb equal to beta is here and h0 h0. So that means this position xb actually is not this xb. So this xb, what's happening? What's wrong here?
They say that this xb is x is beta times is the function of x equal in black there above. So x equal beta plus times xb. So it's a function of x.
Actually, there's a problem. I think we should work this one out. We should check whether it's true or not. If it's not true, then maybe it's from the s is equal to beta multiplied by x.
That's fine.
Because this side is, I think this side is okay.
Yeah.
Because after we found it, then
Yes.
we found the s we were easy.
Yes.
So maybe if it's from the first one.
So you see here, normally we use xb equal to cb h0. Here is here, something is wrong. Is the equivalent rectangular stress distribution S equal to this by B. So we go back to see the definition of the beta. So beta equal to x divided by xc. Yes, this here is the definition is no problem. X is the equivalent height of the stress block, rectangular stress block, and xc is the real compression height. So we try to find where is the problem. Now, if xb equal to xc, xb, the height of compression zone, xb equal to cb h0.
But actually, XB and XC, they are not the same. Are they the same? XB and XC.
XB and XC. It's the same, just the XC is not XC represents the real compression height of the concrete. XB is the boundary compression height. So AB or AB, we all can use XC, but AC normally we use XB because this is the boundary condition. And B normally is the boundary. So actually, till now is no problem. CB equal to XB divided by H0. Actually, is used for the boundary condition. That's correct and no problem. Whereas XB is the height of the concrete compression zone when the boundary failure occurs. And here, the question is here. For the limit height of compression zone equivalent, here they use this X equal to bed XB
for the rectangle equivalent.
So this duration actually still no problem because better we see x divided by xc. So the corresponding b should be cb equal to now we use x divided by h0.
Yeah.
Actually, this formulation is something.
Because actually from the beginning, they never gave any relation to the CB beta. You see, from the beginning, like the formulas, we never saw any relation with the CB and beta. But only just they just brought the beta with the CB.
But here they try to make this relation between them. Where we make this relation is something.
I think the two conditions. You see the two conditions, they are different. I think they're different because here also is for the first condition.
Or maybe the X represents like two different things.
No, he said it's the same, but the case are different. You see, the first one is the boundary condition.
Yeah.
Right? So it's a boundary condition where it's the age of the concrete. But in the second time, they say that the limit age of the compression here is a compression zone of equivalence rectangular stress distribution. They say here the X actually is B, and also the ESB should be now is different because the cases are different. I think it's the same.
X equals B 0. Actually, this part, something some symbol they make mix. The book, on the book they also rather like this. Actually they use x equal to bet so strange.
It's the same.
Maybe it's a mistake there.
I think actually this beta is not the one they defined before. Because on book they also use xc equal to xc. That's not correct. X equal to bet xb. In our book, they give this relation. Then they got this x cb equal to xc divided by h0 equal to bet xb divided by h0. So they replace xc use bet xb. Is just like here x here x use this x from the definition of bet equal to x divided by xc. This symbol C and B some confused.
That's why I was trying to ask that the x and the x maybe they are different.
Yeah. So they make the front part and the lower part of the content they don't make the uniform of the symbol.
Yeah.
So some here we find it's not actually this symbol is not uniform.
Yeah. Because they first use x over xc and right now they are using xb.
Yes. Anyway, we know it, so later on I try to find out the real problem. And finally, they use this formula because in this formula, this symbol or this coefficient is only related to the material. Those things related to the reinforcement, and if you CU related to the concrete. Normally, if you CU, we use 0.0035, and bet, and we can find from the book, from the code. Then, finally, according to the material and the reinforcement, we can got different value from the CB. So, when you do the design, once you have determined the material, the concrete and the reinforcement, then you can check the code to find the CB, the value. CB, once you got CB and you know the dimension of the section, then that means you know the relatively compression height of your design. Should we have a break?
Do you have
15 past 9.
okay.
A little break. Oh.
老师，今天是我的生日快乐。
What?
今天是我的生日快乐。Spring.
It's birthday
It's my birthday.
Birthday?
Yes.
of him.
Really?
Yes.
Happy birthday.
So say congrats.
Your birthday? Yes. Yes.
You should buy us like
You listen.
You don't have party or
Yes.
something?
Have a party, okay?
you should send us to it's a great thing. Buy us bread and egg. Everybody. Jack.
It's not my birthday.
But you make it not much. Not a rich man.
Where is my gift? Yeah, check.
Not a rich man.
This birthday.
Happy birthday to you.
Yeah.
Thank you. Happy birthday to you.
How we sing happy birthday to you? One Kevin. One guy like
Shoba Joba.
Shobo?
Shoba Joba.
Shobo German. Shobo Germany.
And we also need to make sure your design reinforcement is larger than the minimum reinforcement ratio. So avoid the failure mode of the under reinforcement beam. You should make sure the minimum reinforcement ratio you design should be larger than this. And this minimum reinforcement ratio, actually we got this value for the maximum 0.2 and 45 FTD divided by SD, and take the larger one for this value, because this value is got from some of the experience and calculation, and also consider the temperature change, shrinkage stress, as well as some of the design experience. And finally, we got this value. So we should remember when we design the appropriate reinforcement design ratio is in range, because the maximum value and the minimum value when design, you should make sure the reinforcement ratio is in this scope. And actually, last class we have introduced some content of this single reinforcement rectangular section, and these three balance, or the force balance and the moment balance, these three formula we have learned. So for these three, this one is the balance of the tensor force and the compressive force. It's I think it's easy. And this one is this two is the same thing. Just got the gamma 0 and B. It's the external load induced moment. And this part, the right part, is the internal force or induced moment. This way, FCD, the compressive strength of concrete. Bx is the equivalent rectangular block for the compressive stress. Bx is the stress or the compressive stress. And multiply FCD equals the compressive force. And then H0 minus half x is the arm for the compressing force to the. This arm is from the compressing action point to the steel reinforcement. Here is the tensile force Ft. Here is the compressing force Fc for use distance. The arm is like this. The height of this compression zone is x, and suppose this is H0. And this part is AS. So this formula and this formula is just based on the balance of the moment, because suppose this is the half of the beam is in this surface. If you cut the beam from this section, the external load induced the moment should be balanced by the internal force induced by the moment. Then you can make this structure balance, keep stable. So this three formula is the base for our calculation actually. So from these three formula, we write down these three formula. First one, FCD Bx equal to FSD and AS, because this the second one, and come 0 and D smaller than this. FCD Bx 0 minus half x or Fm and D smaller than FSD Bs and the H 0 minus x. These three formula. MU is equal to this. You cannot just write down this line is equal to MU. Doesn't matter. The main thing is this formula actually. So in the book, the number of this formula is 311, 313, and 314. So this one is 3, 7, 313, 314. This 3 formula is the base for calculation. Is this equation? This 3 equation is only suitable for the heat run, is a properly reinforcement beam, and also not applied to the over reinforcement. Because when the over reinforcement field, the actual tensile stress doesn't reach the design tensile stress, so the XD cannot be used. So in order to avoid over reinforcement, the height of the compression should be smaller, x smaller than C. X should be smaller than C0 or CB, H0. So this is the condition. Just now we talk about the compression height should be smaller than the boundary height XB actually. Normally we use CB H0 equal to XB, something like this. SB should be smaller than this thing. So where CB is the relatively limit height of the compression zone and can be referred to the complex stress and the type of the reinforcement. You can find this CB in the table is in code. We just said when you determine the material, you can find the CB in the code. Then from the equation 3 to 11, it's easy to go to x, the compression height x. The calculated tips for the compression zone x can be represented like this. Just remove to this side FSD AS divided by FCDP, then we can get x. So the relative height of the compression zone C is XC, x divided by H0, and then finally we got C equal to rho, and FSD divided by FCD. Rho is the reinforcement ratio. FSD, FCD is the strength of the reinforcement and the concrete. So C, the relatively height reflect one is the reinforcement ratio, another one is the relationship between the strength of the material. From this, we will not only reflect the reinforcement ratio, but also reflect the strength ratio of the material. So it's C is also called the reinforcement characteristic value. And a more general meaning than this reinforcement ratio. When this C equal to CB, the maximum reinforcement ratio we can get. So you see how we got the maximum reinforcement ratio. Once you determine the material, you can find the CB, and you know CB, and the strength of the material you also know. Actually, that means you know the maximum reinforcement ratio have been determined. And also we know the minimum reinforcement ratio. Then when you design, you should check if your design is over or in this range, or in this reinforcement ratio range. It can't be larger than this, it can't smaller than that one. So you should check this value. So from this formula, we can calculate the maximum reinforcement ratio
for the under reinforcement.
Also for this over reinforcement, if the reinforcement ratio larger than this one, that means it's an over reinforcement. So you should make sure you design smaller than this. So clearly, reinforcement ratio should be meet this requirement. here this is wrong. It's appropriate reinforcement. This anti-reinforcement is wrong. No. So that's and also you want to avoid the lower reinforcement or anti-reinforcement. The reinforcement ratio should satisfy. So this one, anti-reinforcement. What do you think is the real meaning of this? It's because I found in this book,
Almost everywhere.
they use many times for appropriate reinforcement. They use the meaning of this, and then they use the lower reinforcement as the too less reinforcement. And for this, use this word to describe the appropriately designed. So it's sometimes confused. But you should know, when we design, we should make sure rule smaller than the maximum and larger than the minimum. So it's easy. The calculation method, how the calculation of the normal section of the reinforcement concrete beam is usually conducted on the control section of the component. What's the meaning of the control section? For one of the simply supported beam, which section is the control section? Control section actually means at this section your internal force is the largest one, most important power section, or most dangerous section.
In the middle.
So of course in the middle is the largest moment section. And also for the shear force should be just near the supporting. So this is the control section for the structure. But if this is the simply supported beam, but if it's a continuous beam, so at this point it also the control. So that's depend on your structure system. Depending on the internal force or the moment distribution or the shear force distribution of the structure. When you design, you should make sure every key point or dangerous point, you should make it safe. For equal section flexible member, the control section corresponding to the largest design value of the combination moment. For variable section flexible member, except the design value of the maximum combination bending moment. Control section also include the section that have relatively smaller size but a relatively large design value of combination. So that means for this situation, your section is all this span is the same, but some special section is like this. Maybe your beam is like this. They use this type of beam. Maybe this is a supporting point. This is the middle span, but at this position, maybe it's more dangerous.
Yes.
So that's the size of your section is changed. This some situation, or sometimes you just change your dimension of the section. So that's not only depend on your movement. Maybe at this position the movement is not the largest one, but the dimension of the section is relatively smaller. Then the result stress maybe is more dangerous than the maximum moment position. So calculation of the loading carrying capacity of the flexible member, meaning to the design section and the check. So first part is design, and the second part is check. That's not means you design is okay. After you design, after you determine the size and the reinforcement, and then you should check it to see if your design is okay. If this design doesn't meet the requirement of the code, and then you need to change the size or change the amount of the reinforcement, something like this. So first part is the section design. The design items should include selection of the material, determine the section size, and reinforcement calculation. So the first part of design of this section includes 3 different contents. First, you need to determine your section. That's very important. I'll ask you to build a bridge, very simply small beam. Maybe tell you the span is 20 meters long, and tell you the width, maybe the width is maybe 10 meters wide. So it asks you to design what type of section you use. So if you now ask you to design one bridge, and this bridge we need 10 meters of width, maybe 10 meters normally we can use as 3 lines, or normally 10 meters only divided by 2 lines. This direction one line, this direction one line. And this 10 meters wide bridge, what type of beam you use? If you design, what type of
The
T beam?
steel.
Steel?
No, T
Yeah.
section.
T section.
T section.
T section is okay. And also you can, if just 20 meters or 20 meters span, sometimes we can use the plate or the empty hollow plate. Okay. Maybe some circle hollow plate for beam. Actually, this belongs to the plate, not the beam actually, because the height maybe nearly just 1 meter high, and the width maybe 1 meter wide, and then you make many pieces of this connect together, just like the T-beam. Normally, T-shape is used for bridge 20 or I think 40 meters, smaller than 40 meters, you all can use T-shape. Even 50 meters sometimes they use, but of course they use a pre-stressed T-shape. Normally 20 meters, even 30 meters can just use reinforcement concrete. It's not necessary to use pre-stress, but use pre-stress is good. But the construction is relatively completed compared to the reinforcement. So the first step, you need to determine the section, the shape of the section, the size of the section. If you use T-shape or use the rectangular shape beam, so the width, the height, the thickness of the plate, something like this, you should determine the size include. And then, of course, the material. First step, you should determine what material, or C40, C50, something, and the reinforcement, HRB 035 or something like this. So what type of material you have, you can use, and then determine the size of the section. After that, according to your size, you calculate the external force, combination of the load, find the maximum moment, and then you calculate how much reinforcement we need to put inside to check the reinforcement ratio. smaller than maximum value and larger than the minimum value. So that's the first part of section design. Section should be designed to meet the requirement that the bending moment capacity MU is larger than the calculated value M. Or here MD. That means your resist capacity should be larger than the load induced by the external force. The loading carrying capacity will determine the quantity of the processing steel reinforcement is at least equal to the calculated bending moment, and so the basic formula is used for crossing design. It's generally to take, because here we use smaller or equal. So when we design, the basic thing, you can use this equal. So for the real situation when we design, normally we will meet these two different situations. One is the given conditions, the calculated value of the moment. So the external load induced moment will give we told you, and the concrete and steel material strength will know. Actually, this is easy. Once you determine what type of material you use, those strengths you can check the table or the code or something. You can find these strengths. And also tell you the cross section. Maybe I told you to design this grid, use the rectangular shape and the width and the height. All told you, and you cannot change it. You must use this dimension. And then the only thing you need to do is calculating the steel bar, how much steel you need to put inside. So for this situation, actually, this is the most simple situation. Just the calculation is ES. So this is the most simple situation. But most situations, the dimension doesn't tell you. You should design the dimension. So this is sometimes we will give you this dimension and just ask you to calculate the AS. So for this situation, namely two basic equations for 0 to unknown x. Because here, see this three formula, everything told you. B, FCD, FSD, all know. And in this formula, this part, W0 MD is given to you. And FCD give you B, will give you, in this side, say, this two formula, X you don't know, and AS you don't know. Two things you don't know, but you got this two formula. So it's easy to just solve this. Because the unknown, this unknown, how say, point, what's this? The number of the equation is equal to the unknown symbol or something. This quantity, variable. Yeah. So this is easy to get the result. So the given environment condition is used to determine the medium cover thickening. And the gamma 0 is based on if you do this solution. First step, you need to assume AS. Because in this formula, H0 also engage That means AS you don't do. So before your calculation, the first step you need to assume one AS. So this is mainly according to your experience. For B, generally AS equal to 40 millimeters, one layer reinforcement. Or if it's two layer, it's 65 millimeters, something like this. Because you see, AS is the central of the steel to the surface.
Center to center.
Center to the surface of the beam.
The central.
So that means if you use AS equal to 40, and if the
this is clear cover. This is clear cover.
no. AS not equal to the cover thickness. Should AS minus half of the diameter of the reinforcement because it is from the center to the reinforcement. Cover thickness is from the surface of the reinforcement to the surface here. So AS is larger than cover thickness. For one layer is more half the diameter. If for two layer, in the middle, in the center of the cell, we have introduced how to calculate AS. For one layer is easy. Two layers, if it's three or more layers, you should know how to calculate AS. Because at the first step, we just assume AS. Once you determine the AS reinforcement ratio, and then you put the steel inside, you have to calculate the real AS to see the real AS and the value you assume the distance. Yeah, so to check if it's okay or not. So the first step, assume AS for this situation. For slab, generally AS equal to 25 or 35 millimeters. And then we use so X or CB. From the basic equation, gamma 0 and B equal to this, we have X equal to just this so. Do you know how to call this so?
You made the S the subject.
Yeah, because in this equation, X is a square. It's a how to call it? It's a 2 yuan 2. Check how to say it. It's in mathematics. 1元24方程1元20方程 quadratic equation univariate quadratic. What's this? Is this quadratic equation? Do you use this word?
Yeah, but what we're talking about is like, is it square of two variable?
Two variable.
Like squares of two squares.
So something like this. X squared minus ax squared minus bx minus c equal to 0. Okay, how do you call this?
Equation of second.
Equation. Quadratic equation. Yes. Quadratic equation is something like this. So this one is just like C. It's x squared and x and get some constant value. Then you go to the result x.
Yeah.
For this equation, do you know the result? Ax plus bx plus c.
Yeah.
What's the result? X equal to what?
X1 equal this. If the B
X equal to
base BC.
To what?
BC. Yeah, X equal BC.
You remember?
So
Like you find the number which when you multiply, you get the square of x. Then if you add, you get the dx.
B is delta.
I forget. I remember it's very easy answer. I check this.
It's common or move the left side.
X equal radical, cubic radical, Baker, B square is 4AC.
Is this?
Yeah.
Yeah.
Is this one?
Yeah. This is the delta. This is the X. This one.
Yeah. So we just use the formula. Then we can get the value of x. And then we got x equal to h0 minus distance, or we just try divided by h0, then equal to c equal to distance. So from this we got x, and once you got x, then ax is easy. In this formula, everything you know, expect ax, then you can find ax. So it's a finished calculation. So the third step, check x. Once you get this x, we need to check if it's less than boundary condition. If it's larger than this, that means it's a over reinforcement. We should make sure it's smaller than CP H0. So from the basic equation, then we can calculation AS. Once this is satisfied, then we can get AS. And then once you get AS, this is the total area of the steel reinforcement you need. And then once you get AS, you need to select what type of the steel you use, because we got very different. As the diameter 20, 22, 24, something like this, lots of different type. Yeah. So that's at this step you need to determine what type of the steel you use. So the diameter and the number. Make sure your total area at least equal to AS, larger or equal to AS. Then check the reinforcement ratio. First, you should make sure it's larger than this minimum value. But here you should see AS is the real amount of the reinforcement ratio, because the first AS is the result of your calculation. But when you determine the number and the diameter of the steel bar, this real AS may be have a little bit difference with the result that you calculate. You cannot got this very correct value equal to this, because the diameter of the steel is fixed 20, 22, 26, something like this. Maybe it's a little bit smaller than this value. Or no, should not be smaller, at least equal. Normally it's larger than this value. So when you calculate the reinforcement ratio, you should use the real AS. So how much the reinforcement you use. If rho smaller than minimum value, then you should use the minimum value. And then AS equal to this. If you find that, but this relation is very real. All in all, we should make sure your reinforcement ratio larger than minimum value, larger or equal, and then smaller than the maximum value. Oh yes, a break. Break, half-hour break. You have an issue, then you need to recalculation. if this AS assume smaller than AS actual, then that means H0 assume larger than the H0 actual. That means this selection is not safe. So then for recalculation, then draw the reinforcement diagram and check the construction requirement. Maybe the spacing of the reinforcement, something like this, and the color techniques. And this the first situation. Everything I have told you, only the area of the stair bar you don't know. This is relatively simple, easy question. But the second situation, given the value of the moment, the external force induced moment, and I also told you the material, FCD and SD, and then ask you to design. Then at those type of questions, you need to design, first determine the size of the section, and then design, calculating the area of the reinforcement. So compared with the first situation, the first possible situation, this is more complicated because the dimension you don't know, you have to design yourself. So in this question, for this parameter you don't know, for unknown variable. So for this type of situation, how to do calculation? First, parameter B, the width of the section, is normally determined by the structural construction requirement, because B have a little effect actually on the loading carrier capacity. The effect is limited. So the dimension B, the width of the section is normally determined according to experience and the construction requirement. Assume rule also here, here assume the reinforcement ratio, not AS. But as general economic reinforcement ratio for a slab, normally rho equal to 0.3 or 0.8%. For rectangular beam, normally is 0.6 to 1.5%. For T-beam, 2 to 3.5%. This value is according to the experience. Actually, for the design of the civil engineering, most time we need to rely on the experience. Especially this situation, the dimension you don't know, then you have to rely on those experience to determine the first stage. It determines some of the size of the section, and then do the calculation. If it's not suitable, and then change a little bit, and then calculation again. Just repeat your process to calculation. And then, once you have assumed the reinforcement ratio, the material will get given to you, then using this formula, we can get C. Once you got C, then you can go this X, the compression height X. So this formula we have just introduced in the last class.
Yeah.
Then from this basic equation, we can go to H0, because here X we got, we know. In this equation we can use C to represent X. Then we can calculate H0. So it is needed to estimate the parameters AS. Selecting H equal to H0 minus AS. So it needs to be rounded. So still we need to assume AS. But compared to this first situation, firstly we need to assume reinforcement ratio and then AS. So now we have determined B and H, then the dimension of the section you have got. Then once you know BH, becomes the first situation. For example, the calculated moment at one type environment at the shift level 3, that means the gamma 0 equal to 0.9. The section size give you, concrete is give you, reinforcement is give you, and no AS, ask you to calculate AS. So this is the first situation. Everything I have to do, just ask you to calculate AS. Then we see how to calculate this. First step, assume AS, because this is a beam, rectangular beam. The dimension is 220 and 500. Then assume AS equal to 44 millimeters. You should pay attention. AS is not a complete cover. It's a cover minus half of the diameter or half of the. If one layer is the half of the diameter. If 2 or 3 layers, then it's the central. Let's see. So you should know AS is not equal to the cover thickness. Then H0 we can get equal to H minus AS 4, 5, 6. Then the step B, from the table we can check the strength of the component steel FCD, FTD. So in the book, once you get the book, actually in the book at the appendix, we got this table for different material and different.
The H0 equals H minus AS. F50 minus 44.
Yeah, 400, 500 actually. Because the given condition is H equal to 500. So here H 100. Yeah, this is a mistake. Shit, I must check it. What? So check the table. Once you got the book, you can check the table, find the strength of the material. Different grade have different strengths. FCD equal to 9.2 MPa. FTD equal to 1.606 MPa. Then, once you got this value, you can calculate Kc. Kc equal to 1 minus distance. So actually, here is use the formula. It has this is the equation. You can go to x or calculate C. Because x divided by h0 equal to C. So once you got this C, actually CB is the boundary condition. You can find that in the code. And now the C is the real situation, real design, and compare with the boundary condition. If it is smaller than this one, that means it's okay to meet the requirement. It's not over reinforcement. So for this CB, this table, we should make sure it's smaller than this CB. And then select this E3 once you got this, you need to calculate the AS. So here, just miss one step. Before this, you should calculate AS. But AS is easy because once you know X or CV, you just use this equation to get AS. Okay? So once you got the AS, then you select the real reinforcement you use. Now in this question, they select 3 and with the diameter 28. So the required medium beam wise is cover on the both side minus plus bar diameter plus clear distance. So you see B, the width should it's 2 multiplied 30 and plus 3, the diameter 28 and minus plus 230 equal to 204 millimeter, smaller than B 220. So that means satisfy the requirement. And then calculating the reinforcement ratio, AS. This AS is the real, is the diameter, is the area of this 3 reinforcement with a diameter of 28. This is 1847. This AS is not the value from here.
Oh, so actually this one is not a raw one. The AS in this equation is not a raw AS. Like
this is the theoretical one. You should large or at least equal to this. Normally it's larger than this one. And then you find the reinforcement ratio is 1.84%. Of course, it's larger than minimum value. And the max value, or the minimum value is this value. It's 0.245. Is the maximum value between these two, 0.2 and this value. And finally is 0.245. Of course, the real reinforcement ratio is larger than this one. It's meet the requirement. Then we got the real AS. Because at the beginning we assume AS equal to 44. But now once you select the reinforcement the diameter 28, then the real AS arrangement according to the arrangement is with the cover thickness 30 and the half of the diameter is equal to 44. So that's just equal to your assumed. So that means it's correct, it's good. So that's the arrangement of the reinforcement in this section. The AS equal to 44, height of 500, width 220, and use 3 of this diameter 28 scale bar. So if the engineer modify the design, the first scenario is to increase H, second is to increase FCD, and the third one is to increase FCD and B. Normally, so what's this mean? So in some situation, if once you check and find that it's not satisfy the requirement, then you have the choice. The first choice is to increase H, increase the H of the section. And the second choice is to increase FSD. And the third one is to increase FCD and B. So that means after you design, and then you check, find the result is not satisfied, cannot meet the requirement of the code, then you have to change your design. The best way is to increase the height of the section. If the height of the section restricted, you cannot change it, then you can increase the FSD, the grade of the reinforcement. And also, if this is also cannot change, then you can increase the grade of the concrete and the wax of the section B. So this is the sentence. If you want to change your design, it's better change the height first, and then change the steel strength, tensile strength of the steel, or the last step to change the concrete grade. So that's different choice, but according to this sequence, you can go to the good design quickly. So this formal part is the calculation of design, and then we need to check your design, including design and check these two parts. The formal part is just the design, and the lower part is the check, section check. The purpose of the section check is to check that whether the loading carrying capacity of the design section meets the requirement or not. Meanwhile, check whether it satisfies the construction requirement or not. So the construction requirement normally the cover thickness or the distance between the steel bar or something like this. So given the section size B, H, area of the reinforcement bar, PS, and the concrete steel, the strength FS, TD, and then you calculate the loading carrying capacity. This is so simple. Everything I told you, just calculating this thing. Calculating the MU. And then first check the structural requirement, structural construction requirement. AS now is known. Once you determine your design, AS is known. Yeah, this equation is how to calculate AS. We have introduced this before. I'm not sure if you still remember or not. Remember?
Yeah.
Okay. So if you got this 2-layer steel bar or 3-layer steel bar, how to calculate AS according to this value. And check the third check the ratio should be larger than the minimum value. And from the basic formula, we check this x should be smaller than xb. Check the condition should be or xc smaller than xb is equal to x smaller than xb. If xc larger than xb, then means the structure is over reinforcement. When xc larger than xb, only xc equal to xb is taken. Most therefore cannot play the rule. Then x equal to xb h0, and this time mu equal to this fcdbx, and fcdb x equal to xb h0, and x h0 minus half x. This x equal to here, x equal to xb is the boundary condition. The mu is the maximum loading characteristic of the single reinforcement rectangular beam. When they calculate the value mu smaller than m, that means your design is not strong enough. Because m is the external load, mu is the resistive force. If you resist force smaller than the load effect, then that means your design is not correct. It's not strong enough to resist the load. So you need to improve the concrete strength, change the size, or using double reinforcement to increase your loading capacity. When satisfied, then from the basic formula, MU equal to FCD BX H0. Actually use the same formula, just X. If it's over reinforcement ratio, if it is over reinforcement, for this situation, the loading capacity, we use this formula to calculation. If it is appropriate reinforcement, the same formula, just the X difference. In this over reinforcement, X equal to Cp H0 is the boundary height. But for this Cp smaller than Cp, here X equals to the real height, real X. So that's the formula to calculation the loading capacity MU. MU should larger than the loading effect. Okay. That's fine. Maybe we finished this book. We haven't got this textbook. Now we have this is the 7th club. That means we have finished half of the all together 10 weeks. Now the 7th is the 5th weeks for our class. That means we have half of this work class. We still haven't got your textbook. Okay, for example, here goes another example, section check. The rectangular section beam with size of BH 200 and 600, concrete strength is C30, and steel strength HRB 335, AS 1245 or 1250 mm square, and arrange the steel by the 3 of 520 and the 2 of the 14. The range is like this. So ask you to check. Now the question is here. So how to check? We go back and say again how to check. First check the construction requirement. And the second calculate the AS. Once you got the AS, you can calculate the reinforcement ratio. Because reinforcement ratio is equal to AS divided by BH0. Once you got the AS, then you got to know the H0. Then you can calculate the reinforcement ratio and compare it with the reinforcement ratio with the minimum value. And then you can calculate the compression height X and compare it with the XB or CB. And then calculating the loading capacity MU to see if the MU is larger than the requirement. So if you don't see the process, ask you to do this Can I see? First, to calculation AS, check the construction requirement. We just assume the construction requirement is okay. There's no problem. Then the second calculation is the AS. AS, the result file 3.53. So now the equation is figured here. So you try to calculation to see if you can get this result. Everyone can do this AS. How to calculate AS?
We take the formula.
Hmm?
We use the formula.
What?
We use the formula.
Which formula?
The formula for AS.
Yeah, actually, we have reduced before. How to calculate AS?
FCD BS over FS.
Use this formula.
Yeah.
Which is this
Yeah.
one.
Yeah. This formula.
Yeah.
Yes, we use it.
So can you get it? Can you look? How to calculate? Or somewhere here to write it down, or go back there, write on the blackboard.
Yeah. Where is the?
Hey, you can write there. You got the chocolate stick?
This one.
Yeah, you can write there. Oh, cannot? Oh, yes, this will go this way. That's true. Or maybe in here. Here.
You want the
Or around there. It's big enough? Oh, it's big.
1000.
Everybody should know. Because I introduced again. You cannot just look at.
Can I?
上了。
Only the line is right there.
Okay, this one.
If you use different type of studio, maybe HRB 335 SD inside. Yes, right? But in this,
Now shape. So the first force is related to the.
this signal should also be SDI, Mr. 1D.
They both should be D. Because D.
Because we only use one type of studio, it's an HRB 335. So actually, you don't need to consider FSD. You just
It's the same.
yeah, it's the same. But if the patient told you they use different studio, HRB 35 and HRB 400, then you need to consider FSD. But now in this question, you can just neglect it, just remove it. Yes, yes, and yes.
So in the question S, the verb is the same. We will not need to use the force.
Hmm?
We will not need to use the force, the different force.
4?
Need to use it, you see?
Now in this question, the F strength is still
Yeah.
actually the same. So we can just remove it.
Oh yeah, okay. So let us see. That will become This? Yeah? Oh, we just need to use this.
Yeah. Formula is not only related to the also related to the steel steel strength. So it's better to get your textbook quickly. So 11:30. So break. Issue in the okay.
Yeah.
Explain. Okay. We are calculating the AX which is this is the B, and in the question they give us so we are it's asked to us actually to find a distance, to find the HO is what? HO
H minus
H is
HO.
HO plus ES. AS
Is
the
minus.
distance.
Is minus. HO minus.
No, it's plus.
Are you sure?
Yeah, H is the so HO it will be the distance from here to there, and AS should be the distance.
I mean the formula.
This one is
No. The formula H equals HO minus AS.
H is actually equal this, but HO
Oh, okay,
is down
okay.
there, is down there. Because H is the distance, the total distance.
Yeah.
Actually, we have to find the distance between in this middle to here. This distance is what we call AS. This distance is AS.
1.
No, AS is AS. Is AS the big AS?
Oh,
But
yeah.
now, but now the distance from the first line of bar steel to the bottom of the B is AS1, and the distance between the second line to the bottom is AS2. So we find that there is a distance between the first line of steel, this one, to the bottom is S11, is AS1, and the distance between the
Second layer.
second to the is S2, and the middle, to find the equilibrium between them to the middle. So the meters between the two lines of bar steel to the end is what we call AS, and it's what we have to find. We have to find it. When we find it, it will help us to know the distance that we have to have, because the distance between here, I will show AS and the distance from AS to them is HO. So we have to know this distance. When we will know that, it will help us now to put the bar steel, so that we may maintain, we may reinforce the So this is actually what we know. We have firstly to, in resolving the problem, when we have to resolve the problem, we have firstly to check the condition, the requirement, the condition, the structural requirement.
The size.
Yeah, we find if it's actually is corresponding to what we want. After us checking it, we have now to make the calculation. And now we're in the place of calculation. So in the place of calculation, for us to calculate, we have a formula, some formula that we have to have in mind. Firstly is this great formula. This formula will help us to find the AS. Because if we find AS, it will help us to know the distance we have to put between the beam, between the steel, and also it will help us to know so that we may reinforce our concrete. And this is the formula. This is the formula. The formula is AS equal the summation or the sum of FS DUPA ASE ASEL and all these things. So I will explain it as we are going. So we have to put in place all the details that they give us in the problem. The first things that they give us in the problem is that we know the kind of steel we are using. They say a rectangular section beam with a size of 206. And that's all the details there. They give us that the H here is 600 millimeter, and the B, the distance in the top is 200 millimeter. So we know those two distances. So we know the size of the beam. And then after they give us also, they say concrete strength of C. We understand that they give us the kind of the concrete we use here. We use synthetic is the kind of concrete we will use. And the steel strength, and for the steel strength they give us the kind of strength of steel that we use. The kind of steel is HR 335. And we know that, and we know they give us also the area related to this kind of yeah. They give us the area with AS 1250. The detail concerning the steel bar. They say the first line of steel bar we use 3 steel bar of the diameter 20 millimeter, and the two headers of the second line we use 2 steel bar of the diameter 40. So those will help us actually to find now the solution that we want. How we can now apply it in the formula. Okay, so let us now apply it in the formula. After us getting all the information that we need, we analyze that in the formula. I have distributed early, and I will do it again so that we can see. Yeah. ES equal the sum of FSD and ASD and AS. So we understand that when we do the summation of the first line and the second line, when we see FSD or when we see FSDE, ASE, RSE, all these things is related to the line, the number of line that we have, the number of line. So here we have 2 lines, means that we have FS D1, RS E1, RS E1, RS E1 plus Fs D1 RS E1 D2 RS D2 and RS E2 divided by here also we take RS E1 multiplied by Fs plus RS E2 multiplied by Fs E2. So this is what we will do. This is what we will do. We understand that I put it 2 because we have 2 lines of the steel. The first line is here and the second line are here. So first line and second line. Now when we put it, we have now to find like the value. What is the meaning of all those values that we find? So as I put it in the program, FSD1 is related to the strain. Is related to the strain of the beam, of the strain of the concrete we use. Can I get the book? Thank you so much. Okay, let's try. Okay. They give us here the standard value of design of reinforcement. So they give us the strain. Here they say design value tensile strain. This is for the steel bar. They give, and for the this is. So we understand that we are here. We are the kind of bar, as we noticed that in the problem, it was the kind of bar was HRB 335, and we come to find here HRB 335, we come here, the design value of the tensile strain is 218 is the design strain of the tensile strain. So this is our case. And we understand that all the steel bar, for this particular problem, we use the same steel bar for everything. So in this problem, the FSD1 will be the same for everything. I repeat, because in this problem we use the same steel bar, the FSD1 will be the same for everything. So FSD1 will be the same, or with FSD2 will be the same. Both of them will be the same. Mean that those kind of steel are the same steel we use here, the same bar of steel, the same type. So it will be the same for the first line and the second line. Here it will be the same from here and the same here from here, FS1. So RS1, what is RS1? RS1 also we find it actually in the book. Is the area of reinforcement in units per meter. Is the area of reinforcement. Huh? Is the area of reinforcement for the first area, like here. And when we come here, we find that the kind of steel we use for the first is the tree diameter 20. This is the type. This is the type of the steel we have to use. So when we use the method we have learned in structural mechanics, we understand that there is something we have to calculate. In the problem we find, we have here, we have to find AS1. AS1 is the distance between, let me explain it here. It's like we have, I will take these parts. We have here those three. We have those three. Those three are the steel bar. And for AS1 is the distance between the middle of the steel to here. This is AS1. See, this is the first line, the second line. For AS1 is the distance between the middle of those bar steel to the end. So we have to calculate it. And there are methods in geometrical mechanics that we can use. But here we have the value already they give us. So we understand that we know that for those three steel, the diameter, the distance between here and here, or the diameter is, for the tree, the diameter is 20. The diameter is 20. As we know that the diameter is 20, surely we can know that the middle, it can be, the middle can be 10. But when we take our book, we understand that if we know the distance, this distance, and we know again this distance, the distance between the bottom to here, the limit of the steel, we will know the AS. So AS1 is actually this distance. This distance, the distance between the bottom to the limit of the steel bar, this distance, we can call it maybe lambda, or we can sigma. This distance sigma plus the distance, like the
A sigma.
yeah, we can say the half of this diameter, half of this, half
Checking
of this
the
one,
book.
half of the diameter of the steel, half of the diameter. But we know that when the steel will be in the beam, the calculation will not be exact, but in the book we can find the value. In the book now they say to us that this distance sigma, because IS1, the distance sigma here
30.
for the tree diameter 20 diameter steel bar is 30. Is 30 when we are in they give us in the problem that we are in the phase 1. We are in phase 1.
And has a cover thickness.
Yeah. So when we take it is 30, and then we will take plus
diameter of
The half of the diameter.
the half of a diameter.
You
And
also
the
check inside the book.
3.20 steel, you can find it here. We have area of reinforcement. We have the let's see. Okay, we are here firstly. We are here firstly. We find that we are in the. We have to find the abutment curvature bin. We are in the bin. So elements type. Elements type is a bin. So you see a minimum cover thinking for reinforcement strength. So the minimum cover thinking for reinforcement is this one. This sigma. Is the minimum cover thinking.
Thickness.
Yeah, thickness. So when we come here for the beam, we see that we are in the first environment is first type. First type is given to us in the problem.
Question.
In the problem given to us is 30.
Yeah.
So the reason why we have put the 30 here, we have already find it. But now it remains to us now to find now the
Half of the
half
diameter.
of the diameter of the steel. So for that,
that's here. 3 diameter 20.
for that we just came here. Is given to us also. We find that diameter. We have the kind of steel. The kind of steel here is the diameter 20.
Yeah.
Wait.
No.
The diameter is 20. It's the area of cross section and weight of reinforcement.
No,
Area of cross section. So we are finding the area of the cross section. is this one, is here. So we have for the
It's not that.
diameter. The diameter is 20. 20. The two still, the diameter is 20, and we come here. Other diameter
Outer diameter.
is the outer diameter is 20.
22.7.
22.7. So we take,
half of it.
yeah, the outer diameter is actually everything, but we take now the half of that. The half of the outer diameter, which is
22.7 divided by 2.
22.7 divided by 2 is what will give us now the
AS1.
value of AS1. We can calculate it. After calculation is this value
41.35.
41. This is for the AS1.
1.
AS1. We have seen that the FS1, we have already find it. They say is 2,220. This AS1 here, we have find it also. We say is in the book is 942 millimeter. AS1 is what we just find.
41.35
Is 41.35
millimeters.
millimeter. So FS2, FS then D2. We say that as we use the same steel, so FSD1 equal to FSD2. So here also is the same value,
280.
280 millimeter. So AS2, ASE2. What is ASE2? ASE2 we take it in the same way that we took also for the
AS1
AS1. So AS2 we find it also in the
book.
They are both of them. They are the same steel, but they have different diameter. You see, this one. The first line and the second one is constituted by the same steel. Because it's the same steel, they will have the same strength, the same strength,
Design
the
strength.
same tensile strength. Because it's the same steel, they will have the same tensile strength, which is 218. But because the diameter is different, they will have the different area of reinforcement. They will have the different area of reinforcement. I think it's here. Here. Area of the cross section. They will have the different area of the cross section. So for the 40, yeah, for the 40, we understand that for the 40 is here we have two steel of the diameter 40. So here also, you see, we have 40, two steel, the number of steel, two steel, the value is
308.
yeah, 308. So this will be the value of AS2. AS2 is 308 because we have two steel of the diameter 40. And when we come here, find that the area of the cross section, we find that we have the diameter 40, and when we have two steel, the value is
308.
308. This is the area of the two steel. So we come here. It's the same way that for the first one it was 20, the diameter was 20, but the first one it was 3. So the reason why we took this one, the first one ASE1 was 90. No,
942.
yeah, it was 942. But for the second one is what we find here for the
308.
308. So for that we are fine. So we find that we know, and now we will remain just with one thing. We remain to know just the ASE2. How to know the ASE2? ASE2, I say that I will come here again to explain.
You can even write it.
Yeah. we understand that this is the first bar steel, this is the second bar steel. So for AS12, we understand that AS12 was the distance between this and the bottom, AS1.
S1.
So for AS2, it will be the distance between
The second layer to the bottom.
the bottom, AS2. And for us to calculate the AS2, we understand something that we have to calculate the distance between the bottom to here, and we have to calculate the distance also between the middle and here. So for that, there will be two things we calculate. We calculate for more simplification, we calculate the distance between the bottom to here and the distance between the bottom to here.
If you have already calculated here to here, so you just find from here to there. Then it be AS2.
What we will do is mainly the same that we did. So AS2 is the compilation of those two things. So we will do something. This is more about structural mechanics. So what we will do is that we know that as we are using the same bar steel, this distance, we call it the minimum cover thinking for the beam. As we are using the beam, it was 30. It's 30.
Yeah.
So it will be 30.
Yeah. Cover thickness.
We take AS2 will be
30.
we take this is the first one and this is the second one. The first one is the second one. The first one, it will be 30 plus here now. If we remember, for AS1 we use the half, but here we not use the half, we use everything. So we take the out area of
the outer area.
The outer area of AS1. The outer area of AS1 was 2. This is the outer. We have for the first bar steel was 20.
Yeah.
The outer area
22.7.
it was 22.7.
Yeah.
So we not divide it, we take it all. It's 22.7. And then we take plus, this is the first section, and for the second section, what we take, this also is the outer area, the minimum thinking for the beam. We will take again the 30.
Yeah, the cover thickness.
The cover thickness again, there is a cover thickness here. We take the 30 plus, now here for our 2 base steel is 240. And we go now to find the outer area of 2 bar steel of 40, and we divide it by 2.
Diameter.
We have 40 here, the diameter 40, right? And then we find the outer area of the steel bar of 40 is 16.2, and we divide it by 2. 60.2, we divide it by 2. So when we divide it by 2, we find this distance. So when we put it together, we find that the AS2 it will give us
90.8 millimeters.
This is AS2. So now we know AS2 is 90.8 millimeter. So now we know all the unknown of our equation. AF1 we know 280 millimeter. For AS1 we know is 942. We know for the ASE1 we know. FS2 we know that FS2 is the tensile strength. All those things are related to the kind of steel we use. So this is the tensile strength. The tensile strength, because we will use the same steel, the tensile strength will be the same. So 280. AS1 is the area according to the first steel, the area of cross section, the area of the cross section of the steel bar.
Layer 1.
Line 1, yeah, it should be this one. We find it in the book. And ASE1 is the area of the distance between the bottom to the center of the first line of per steel. We find it also. We see that is 41.35 meter. And we have also find again the tensile strength. The tensile strength we see is the same. And AS1, the area of the cross section of the second bar steel, we find that is 308 millimeter. And then we find the AS between the bottom to the middle of the second line of the bar steel. And here is the same value. The cross section, area of the cross section is what is here. AS1 we already have put it here. Tensile strength. The tensile strength.
You know that is
200. AS2 is the cross section of the second line steel, the second bar steel, the cross section of those steel. And then we have also the tensile strength. The tensile strength of it. So when we have it, we just calculate everything.
Put them together.
Yeah, when we put together, we move, check, and then we find the answer. The answer will be this one. As we know the value, we just have the
53.53 millimeters.
And as we know now that we know the AS, and then after that we'll be able to find
The height.
H, it will be
how do we do it?
H will be as we come here again. AS as I say to us. H is this one. Is this distance? The distance.
Yeah.
So the total distance of the beam, of the rectangular distance of the beam, minus AS will give now this distance. The distance from the middle of the bar steel to the top. The middle of the two lines. See, we have the bar steel, the middle, from the middle to the top, H0. And from here to the bottom is AS. And then we put there to find our HO. And then we find it, we have resolved the problem.
Okay.